The cosmic microwave background. For 60 years, it's been the bedrock of cosmology, the unshakable proof of the Big Bang. It's an image of the universe just 380,000 years after its birth. A faint, primordial afterglow telling a story of a hot, dense beginning. We've trusted this story. It has guided our understanding of everything. But what if this picture, the very foundation of all we know, is incomplete? What if the echo of creation isn't just an echo? What if it's also the collected ancient light from a trillion stellar ghosts, a cosmic firestorm that's been hiding in plain sight? Our most powerful telescope has just found evidence that points to this possibility, creating a fascinating new puzzle for the Big Bang theory. And if this puzzle can't be solved, everything we think we know about our cosmic origins might have to be rewritten. To get a sense of this potential revolution, we first need to appreciate what's being challenged. The standard story of our universe begins 13.8 billion years ago with the Big Bang. In its first moments, the universe was an impossibly hot, dense point that immediately began to expand and cool. For the first 380,000 years, it was a searing, opaque fog of plasma, a chaotic soup of protons and electrons, so dense that light couldn't travel more than a few steps without being bounced around like a pinball. The universe, in essence, was a star that filled all of space. Then, a critical transition happened. The universe cooled enough for protons and electrons to finally grab onto each other, forming the first stable hydrogen atoms. This event is called recombination. In a single, universe-spanning moment, the fog cleared. The photons of light, now free from their constant collisions, were unleashed to travel unimpeded through space forever. The universe became transparent. That ancient light is what we now call the cosmic microwave background, or CMB. Of course, it wasn't microwaves back then. It was a brilliant, intense light, but 13.8 billion years of cosmic expansion has stretched its wavelength, redshifting it from visible light down into the cool, faint microwave part of the spectrum. When we look at the sky with microwave telescopes, we see this ancient light coming from every direction, a near perfectly uniform glow at a temperature of just 2.73 degrees above absolute zero. When it was stumbled upon in 1964 by Arno Penzias and Robert Wilson as a persistent hiss of static, it was the smoking gun for the Big Bang. It was exactly what the theory predicted, the leftover heat from a hot, early universe. Over the decades, our instruments got better. Satellites like COBE, WIMMAP, and Planck mapped this radiation with breathtaking precision. They confirmed its spectrum was a near-perfect blackbody, the exact thermal signature you'd expect from a hot object that has cooled over time. This fact alone dealt a devastating blow to rival ideas, like the steady-state model. But the maps revealed something else, something even more profound. The CMB wasn't perfectly uniform. It had tiny temperature fluctuations, hot and cold spots that varied by only 1 part in 100,000. In the standard model, these tiny variations were quantum jitters from the first moments of creation, blown up to cosmic size. These were the seeds of everything. The slightly denser, hotter spots had more gravity. Over hundreds of millions of years, they pulled in matter, slowly growing into the first stars, galaxies, and the vast cosmic web we see today. So, the CMB isn't just a baby picture. It's the genetic blueprint for the entire cosmos. For half a century, its authority has been nearly absolute. And then, we opened a new eye on the universe, the James Webb Space Telescope. Its mission was to peer back into the cosmic dawn and see the very first galaxies flicker into existence. What it found was not what the standard model had prepared us for. It didn't find cosmic toddlers taking their first steps. It found giants. The JADES program began discovering galaxies at extreme redshifts, a way of saying they are incredibly far away and therefore incredibly far back in time. It found one galaxy from just 320 million years after the Big Bang. Then it shattered its own record, spotting JADES GS Z14-0. The light from this galaxy traveled for over 13.5 billion years to reach us. A snapshot from when the universe was only 290 million years old. And this galaxy is a problem. It's not a faint, disorganized clump of early stars. It's surprisingly bright and big, measuring over 1,600 light-years across. Its light isn't coming from a quasar, which is just superheated gas falling into a black hole, but from a huge population of young stars. This implies a shockingly fast and efficient building process, flying in the face of what we expected. Even more shocking was the detection of oxygen. In cosmology, any element heavier than hydrogen and helium is a metal, and metals are forged inside stars. To see oxygen so early means that at least one full generation of massive stars had to be born, live out their entire lives, and then explode to enrich the surrounding gas before the stars we are now seeing could form. All of this crammed into less than 300 million years. According to our standard timeline, this is astonishingly fast. Models predicted the first galaxies would be small, wispy, and metal-poor, slowly growing over 1 billion years or more. Yet, JWST is finding galaxies that are far more massive, luminous, and chemically mature than they have any right to be. They're like bodybuilders in a nursery. This isn't a minor tweak. Some analyses suggest that the number of massive galaxies JWST is finding in the early universe exceeds what should be physically possible, a scenario that would require converting every single atom in the cosmos into stars with 100% efficiency. It's a paradox. The data is screaming that something is wrong with our models of how the first galaxies formed. And this has led some scientists to question not just the details, but the very timeline itself, a timeline built on the CMB. When data refuses to fit a theory, you have two choices: tweak the theory or consider a radical alternative. The discovery of these impossible early galaxies has sparked just such a moment. While many are working to adjust the standard model, a more audacious idea has been proposed by a team of researchers, including Pavel Kroupa at the University of Bonn. What if the CMB is not the afterglow of the Big Bang at all? What if it's the reprocessed light from the very galaxies JWST is now finding? Their 2025 study presents a dramatic reinterpretation of our cosmic baby picture. The central idea is that the faint microwave signal we see might be in part the light from ancient galaxies, absorbed and re-radiated by cosmic dust. Here's how the theory works. The JWST data suggests the first galaxies formed in violent, incredibly bright bursts of star formation. For a short time, these galaxies would have blazed with a ferocity we can barely imagine, lighting up the entire universe in a galactic firestorm. Now, picture that intense starlight flooding the young universe. It was filled with cosmic dust forged by the very first stars. This dust would act like a universal fog, absorbing the starlight. The dust would then heat up and glow, re-radiating the energy not as starlight, but as a smooth, uniform thermal radiation, like hot coals. According to the team's calculations, this process would create a background glow with a perfect thermal or blackbody spectrum. Over 13 billion years of cosmic expansion, this glow would cool and redshift down into the microwave spectrum. It would look, for all intents and purposes, identical to the signal we've long interpreted as the afterglow of the Big Bang. The researchers calculated that the light from these early galaxies must contribute at least 1.4% to the CMB's energy, which has led them to ask if it could be even more. If they're right, it means we've been looking at the combined embers of the first great galactic fire and mistakenly calling it the echo of creation. As Pavel Kroupa puts it, this could mean the true strength of the primordial signal has been significantly overestimated because it's contaminated by this galactic light. The most profound implication of this new theory is how it reinterprets those tiny fluctuations in the CMB. In the standard model, those temperature spots are everything. They are the seeds of all structure. The warmer, denser regions had more gravity, and over eons, they grew into the galaxies we see today. The pattern came first. This new hypothesis flips that picture inside out. If the CMB is really the collected light from ancient galaxies, then the galaxies came first. So, what are the fluctuations? In this model, they aren't seeds, but shadows. The hot and cold spots we see might simply be the result of an uneven distribution of those first galaxies and dust clouds. A patch of sky that had more primordial galaxies would create a hot spot in the background. A region with fewer would look like a cold spot. This would mean the fluctuations, which we viewed as sacred relics of quantum physics at the dawn of time, might instead be a mere artifact of the lumpy distribution of the first stars. This alternative view also makes us look harder at how CMB data is processed. The signal from the early universe is incredibly faint, and our view is blocked by microwave sources in our own Milky Way. To create those famous maps, scientists must carefully subtract this foreground light. But that subtraction relies on assumptions about what the primordial signal should look like. The critique is that this process risks becoming a self-fulfilling prophecy. If you clean the data, assuming a Big Bang-generated CMB is underneath, you might just be tailoring the result to fit your expectations. Kroupa argues that if you first subtract this newly calculated foreground of ancient starlight, you might find that what's left of the CMB is different from what we thought. It presents a stark choice. In one story, the universe is born from a smooth plasma with tiny seeds that patiently grow into galaxies. It's a bottom-up story. In the other, the universe first ignites in a chaotic firestorm of giant galaxies, and the afterglow we see is just their light, casting shadows on the background. It's a top-down story. The data from JWST has, for the first time, given this second story a foothold in real-world observation. Those impossible galaxies are real, and their ancient light had to go somewhere. Science isn't a book of settled facts. It's a relentless process of questioning. The story of the cosmos is being written and rewritten as we speak. If you believe in the power of following the data, no matter how uncomfortable it gets, then join the conversation. Subscribe for more explorations into the frontiers of science that are pushing the boundaries of what we know. So, has the Big Bang been disproven? The answer is a clear no. The standard model of cosmology is supported by a mountain of evidence beyond the CMB, like the precise abundances of light elements in the universe and the expansion of space itself. It is, by far, the most successful explanation we have for our cosmic origins. However, what JWST has found and what the Kroupa thesis proposes is one of the most significant challenges to the Standard Model in decades. It's not just fringe speculation. It's a direct theoretical response to puzzling, high-quality data from our best telescope. The impossible galaxies are a genuine anomaly that demands an explanation. The idea that the CMB is contaminated by ancient starlight is testable. Future observations will tell us just how many of these massive early galaxies there were, and how much light they really produced. And this new theory has its own major hurdles. Critics rightly point out that it will have to explain the incredibly precise blackbody spectrum and the specific pattern of fluctuations in the CMB, something the standard Big Bang model does beautifully. What's certain is that we've entered a thrilling new era of cosmology. The foundations have been shaken. A crack has appeared. And for the first time, we have a data-driven reason to ask a question that was once almost unthinkable. Are we the children of the Big Bang's afterglow, or are we living in the echo of the first great fire? The universe is under no obligation to make sense to us, and the next few years of discovery will be about finding the answer.